Hello, young people. Today we're going to be talking about accuracy and precision and how we define them in chemistry so that we can use them. By the way, chemistry spelled wrong in this. That's not good. So accuracy refers to how closely a measurement matches the true or actual value that we know. Those true or actual values can be given to you. They can be from material that we've collected. There are lots of handbooks that contain all kinds of values for different things that have been measured over the course of years. To be accurate really only requires that you have one value that hits the bullseye. But the problem with that is we don't always measure very accurately, so we try to do more than one measurement. More measurements is better. So precision comes in because precision means, can we reproduce the measurement every single time with the right exactness? Can we make sure that we're using our tools well and that we know how to do that so that we can repeat the measurement as many times as we need to. To decide on precision, you need to make sure you have multiple measurements, and you need to notice how those true values are and how far away they are from one another, because they need to be close together. Precision is talking about being close together no matter where they are. Accuracy is talking about hitting a target value. So in order to be accurate and precise, this is our goal. It's to be accurate and precise. You have to pay close attention to the details that you're doing, and you have to make sure that you're getting the same results as many times as you possibly can so that you can hit the target well. So, for example, when we're looking at this kind of an idea, we're talking about this idea of like shooting arrows. You know, if you're good at archery, you're good because you hit the target all the time and you're shooting at the same place all the time. Your what they call your pattern is tight. But if you're not hitting the target all the time, or your pattern isn't tight, then you have some issues that have to be corrected. Same thing in chemistry. We want our pattern to be tight, but we want it also to hit the target. So that's what we're talking about with accuracy and precision. So if we look at this, we want to look at these for archers. So this archer has shot his shots, and it says to win the tournament, the archer must hit the target the most times, and the winner must show accuracy and precision. So this first archer has bad accuracy and bad precision. They're not tight together. They're not close to the bullseye. Okay, Archer 2. Archer 2 has bad accuracy. It's not on the bullseye. It's outside of the bullseye. But they're all stacked together. It's a tight group. So that's good precision. If you look at Archer 3, Archer 3 has good accuracy and good precision. They're all really close together and they all hit the bullseye. And then finally, Archer 4 has good accuracy. It's really close to the bullseye, almost on it, but poor precision because they're not clustered together. So who wins? Well, clearly Archer 3 would win here since he had good accuracy and good precision and all 4 shots hit the bullseye. So when we're looking at accuracy versus precision, we also have to understand that this helps us understand the kinds of errors that we're introducing here. Random errors can be reduced by making sure we're being precise. Systematic errors can be reduced by making sure that we're being more accurate. So systematic errors are instrument errors. So you didn't zero the instrument properly. We made the wrong solution. Random errors are things like the temperature in the room varies wildly. So from one area of the room, it's hot, and the other area of the room, it's cold. Those are random. But we also think about it in terms of what we do. So the person running the test is not properly trained. So that's why we do a lot of training. So systematic errors are errors in a single direction. So they're all going to be really high or they're all going to be really low. And we can correct those by calibrating instruments. That's why systematic errors are considered to be errors within the instrument that we have to take care of as the user and recognize that there's a problem and then calibrate to make sure that we understand how far off they are. Random errors, though, are errors that can be in any direction. And this is where a lot of error comes in for people who are not paying attention to the details. So we've learned how to use tools in measurement. But if you don't focus on that when you're doing it, then you're going to have lots of random errors because you're never going to be getting the same number every single time. So it's very important that you understand this. Okay, so to determine this, we have to look at the data. And data is going to tell us a lot. So there are three kinds of calculations that we can do. So when we're looking at targets, we know that determining accuracy and precision is easy. We can see that. We can see how close things are together. We can see if they're hitting the bullseye. We can do that. But when we're looking at data, it's a little different. So the three types of calculations that we can do are standard deviation. That's a pretty complicated one, to be honest with you. And we don't use it very much because in chemistry, to be honest with you, we like easy math. And percent error with averages, making sure that we have averages, that's relatively easy math. And range is relatively easy math. So those are the two that we will use most often in chemistry. Not that standard deviation couldn't work. It can, and you will probably learn that sometime in your math career. I think in Algebra 2 during your statistics unit, you'll probably be learning about standard deviations. So I'm just showing you standard deviation so that you can understand what's going on here. This is the calculation for standard deviation, where X is the measurement, or Xi is the ith measurement, how many ever measurements you made, X is the average measurement, and N is the number of measurements. And you can calculate it. And what we have is we have this idea that most of everything should be right there in the center. That's where everything should be. That's one standard deviation away. And then the green part is two standard deviations away. That would take care of about 95% of things. And then 3 standard deviations away takes care of 99% of things. There's still 1% out there that can be further off, but this is how they actually produce those things on your standardized tests that say, like the ACT, you know, where are you in percentile? This is where that comes from. It comes from a standard deviation calculation. Okay, so that's what standard deviation is, and you can see the explanation right there. Percent error, on the other hand, is an indication of accuracy as well. And what it does is it compares the experimental value, which is your value, to the literature value, which is called the accepted value. Sometimes you will see experimental minus accepted. That's kind of what I use, but it's the same thing. Literature, accepted, whatever. That is the accepted value for the value of the thing. And you can see, or the value of the thing that you're supposed to be measuring. So your value is experimental. We subtract it from the accepted value. Notice that there are absolute value bars. What that tells you is that it's all about the difference. It can't be negative, because absolute value means you're going to take the positive of whatever comes out of that. So it's really important that you make sure you understand that. So here's an example of percent error. A student determines the density of a substance to be 1.40 grams per milliliter. Find the percent error if the accepted value of the density is 1.36 grams per milliliter. So you can see the experimental value for the student is 1.4, so we put that in first. Then minus the accepted value, which was 1.36 grams per milliliter. Divide by 1.36 times 100, and we get an answer of 2.9% error. I would actually say 2.90% error because of 3 significant figures. Okay, so percent error is not hard. You just have to know your value and the literature value or the accepted value. Okay, range. Range is what we're going to use to find precision. Range is basically the highest value that you have measured and the lowest value that you have measured and the difference between the two. So this is something that you learned, I'm sure, sometime in algebra or geometry when you were talking about domain and range. So range is this idea of how far away are my two top numbers, my highest and my lowest. And that value can help us understand, did we get our numbers closely grouped together or are they further apart? So that's how we're going to use that. So for example, the sample is known to weigh 3.182 grams. Jane weighed the sample 5 different times with the resulting data. Are Jane's measurements accurate? So if we start looking at this, if we add up these measurements, 3.200 plus 3.180 plus 3.152 plus 3.189, we get an average of 3.180. So that's our experimental value, 3.180. So we take 3.180 minus 3.182, okay, divide that by 3.182 times 100, and we get 0.06%. So Jane's measurements are pretty accurate. The average comes out to be 0.06% in percent error away from the actual value. So that's pretty good. So the next question is, are Jane's measurements precise? So we've got to look at Jane's highest and lowest measurement. The highest is 3.200 and the lowest is 3.512 or 152, I'm sorry, 152. And we see a difference of 0.048. That's a pretty big difference. That's a pretty large difference in terms of the fact that you're measuring to the nearest 1,000th. She's 4 significant figures away from the nearest 100th. So it's really important to understand that that's a pretty big number in terms of where your place is. Like your estimated place is 0.001. That's 48 times 0.001. That's kind of where it comes out. So that's not very precise. So Jane's not doing a very good job of using the tools that she has. All right, here's an example 2. Okay, consider the data in centimeters for the length of an object as measured by 3 students. The length is known to be 14.5 centimeters. Which student had the most precise work and which student had the most accurate work? So to do this problem, I want you to take a moment and I want you to stop the video and I want you to do the average and then the percent error. And then I want you to do the range. And then I want you to go ahead and come back and then we'll give you the answer. So go ahead and take some time right now to stop the video, calculate the problem, and figure out your answer so that you can compare it to the correct answer. Okay, so now we're back. So the answers are student A is the most precise because student A has a difference of 0.1 centimeters, which is within the range of certainty that we have there because we are at the nearest 10th in our estimated value. So that's pretty good. The most accurate student is C because his results were within 0.12 and 2 were the true value. So we didn't take the average and the percent error there, but we did look at range and we did look at how many values were true. Okay, so wrapping all of this up here, why is this all important and why significant figures are necessary? Because we have to be able to determine if our measurements were done well. We have to make sure that we know how to measure. We know the right ways that scientists are supposed to measure so that we can always ensure that everything that we're measuring is done correctly. Significant digits is so that we don't exaggerate how well we can measure something and we don't overstate what we can say about a measurement. So we have to make sure that we understand how to do that. And it's really important that you take care of that and you make sure that that's done correctly.